All right, welcome back, everybody. I'm really excited today because we get to move into chapter 15. We're on section 15.1 now, and now we're entering the chapter on integration, which is super fun. This is also going to prime us for chapter 16, which is basically like integration, but doing it with vectors. So all this stuff is really cool. Let me pull up the slides and we'll get started. Okay, so there's a little bit of introductory stuff that I want to go over first. I want to talk a little bit about what linear functionals are, and then I want to talk about this this theorem with a complicated name, the Rees-Markov-Kakutani representation theorem. I've talked about this before in previous lectures, like in my Math 8 class, Calc 2, and I talk about it even in Calc 1 because it's just a really, really good motivation for studying integration and the integral. Like, why do we care about the integral, you know? Then we're going to review the mechanics of the definite Riemann integral. This is something that you should have talked about in Calc 1 and hopefully reviewed again in Calc 2. We are going to review it again now, and then we're going to generalize these mechanics to functions of two variables, at least for now. And then as we proceed through the chapter, we will actually, we're going to revise the mechanics of the definite Riemann integral several times as the course goes on in this chapter. And the next chapter, actually. Then we'll talk about volumes and double integrals, talk about iterated integrals, and then how Fubini's theorem relates to iterated integrals. And then we'll finish up by talking about the average value of a function of two variables. All right? Okay, so here's the first stuff. This is a concept that many of you are going to see later on, a linear functional and just a functional in general. So what is a functional? A functional is a function whose domain is a space of functions and whose range is a subset of R. So when we talk about functionals, what we're really talking about is this machine that takes in functions as inputs and spits out a real number related to that function. That's the basic idea. And you've actually been working with these a lot. You've been working with them ever since Calc 1. So for example, the limit operator is a functional, and the differential operator is a functional, and the integral operator is a functional. And what these machines do is they take a function and they spit out a number related to that function. That's really what a functional is. So that's what the general idea of a function is. A linear functional is a functional that also enjoys the properties of linearity. So what is linearity? That basically means that your function will split over sums and differences, and also that you can pull out constant factors. So scalars, I should say, where C is a scalar of some sort. And those two properties are called linearity. The limit operator enjoys linearity. This is what lets you turn the limit of a sum into the sum of the limits, right? So when those limits exist, you can pull them apart like so. You can also pull constants. Oops, wait, this way. Yeah, you can pull constants out of the limit operator. So those things that you know and love from Calc 1 working with limits, that's what I'm talking about. The derivative has the same property, the differential operator. If you differentiate a sum, you can write it as a sum of derivatives. That's this right here. That's this property. Taking the derivative of a sum and writing it as a sum of derivatives. You can also pull constants like scalar multiples out of the differential operator. And then the same thing for the integral. So the concept of a functional and the concept of a linear functional is one that you've actually been playing with for a while, but it's good to explicitly state that that is a mathematical object, that is a thing, that people study. There's literally an entire field of mathematics devoted to it called functional analysis. And many of you are going to end up taking that course later on, a course in functional analysis. So why do we care about these things? Well, there's this really, really important theorem called the Rees-Markov-Kakutani representation theorem. It's named after Frigyes Riesz. He's the one who introduced it for continuous functions on the unit interval back in 1909. It's also named after Andrei Markov, who extended the result to some non-compact spaces in 1938. And then it's also named after Shizuo Kakutani, who extended the result to compact Hausdorff spaces in 1941. So relatively speaking, this theorem is kind of new, meaning within the last, well, at least at the time of this recording, 80 years. So it's not super old like the fundamentals of calculus, right, which are, hundreds of years old. And what does this theorem say? So you don't dwell on all these little details. Don't feel like you need to memorize this or that I'm not going to test you on this theorem. It's certainly not going to prove this theorem. But this theorem gives us a motivation for studying integration at all. So this ties into that stuff we talked about at the beginning of the course, like why should I care about this? Why am I learning this? Well, there's this theorem that, in my opinion, completely motivates the study of integration. So I will read it and then I'll try to make it a little more intuitive in the next slide. Let X be a locally compact Hausdorff space. That just means it's a space with some nice properties. I won't go into the details. Then for any positive linear functional L defined on this special space of functions, in fact, it's the space of compactly supported continuous complex valued functions, then there's a unique regular Borel measure mu on X such that your linear functional can be written in this form for any one of those functions. So by now you should be like scratching your head, maybe gasping at how wild this sounds and how complicated it is. Um, Put it very simply and very concisely, what this is saying is that under certain conditions, any linear functional that you want to explore can be written as an integral. And remember, what is a linear functional? A functional just takes in a function and spits out a number related to that function, right? That's what I'm talking about. And this is saying, hey, if you want a functional that also has the properties of linearity, then no matter what that functional is under some certain conditions, you can just write that functional as an integral. That's basically what it says. It's a little bit easier to understand if we look at Ries's, I was going to say Ries's representation, Ries's statement of the theorem right here. So this is how it was originally defined. Every continuous linear functional defined on the space of continuous functions on the interval 0 to 1 can be represented in this form, where mu of x is a function of bounded variation on the interval 0 to 1, and the integral is a Riemann integral. So this one is a little bit simpler. What it's saying is that if you are only looking at continuous functions on the unit interval, the closed unit interval, then you can write any linear functional that you describe on those functions as a Riemann integral. And this little thing here, d mu of x, just pretend it's dx. Just pretend it's dx to make things easy. But you actually have some more flexibility. It doesn't have to just be dx. It can be d some function of x, some function that has a nice property. And this is actually what we call a set function. And it's basically it's a measure, but we won't go into measure theory now. So what is the big idea? This is the big idea, and this is the takeaway that I want you to have from this discussion. The definite Riemann integral is basically the canonical measuring device. So the Riemann integral is the way that we measure lots and lots of things, pretty much everything that you would be interested in measuring until you get into some really, really deep examples. So things like volume, arc length, surface area, charge of a particle, risk, flux, probability, efficiency, accuracy, all these things that you want to measure. What this theorem says is that you're going to use an integral to measure that. And even if it doesn't look like an integral, it can be written as an integral. A good example is the dot product. So there's a reason that it's called the scalar product, and it's because you can generalize it. And sure enough, if you want to take that idea of a dot product, you can generalize it and it will take the form of an integral. Yeah, so big takeaway here, the integral is our measuring tool. So that's why we study it so heavily. That's why you take whole courses in just this thing, literally, right? Like Calc 2, that's what we're going to do right now. We're going to study the integral because it is our canonical measuring device. So here we go. This should be hopefully a bit of a review from Calc 1 and Calc 2. So this is just the mechanics of the Riemann integral. Here we go. Let's say you've got a function f defined on some interval a to b, and we're going to let p be a partition of the interval from a to b. A partition is just a list of points in the interval a to b, and we have this condition on the list of points that they're they're in order basically. So there's x0 as the left endpoint, x1 is strictly larger than x0, and you keep going all the way until the nth point in the partition, and that will be the left endpoint. All right. Okay, then we're going to let delta x sub I be the length of these intervals. So literally the difference between the consecutive partition points. So delta x sub I is just the length of those subintervals. And we're going to let x sub I star be a sample point that we take in each one of those subintervals. Then we define the definite Riemann integral of f from a to b as this number. And how do we define that number? We define it as the limit of these Riemann sums. So again, just kind of a quick refresher. Actually, maybe I'll flash forward to here for just a minute, and then I'm going to flash back, right? This is the picture that you want to have in mind. Just ignore this for a minute, but just look at this picture for a minute. Stare at it, ponder it. In fact, let me throw up the thinker for a sec. Here, just stare at that picture for a minute, and then we'll go back to the definition. Okay, so what this is saying is, if you want to define the Riemann integral of a function f from a to b, then you're going to take the limit of these partial sums, these partial Riemann sums. And what are these Riemann sums? This is basically the height of that rectangle. Oops, there we go. This is the width of the rectangle. So this expression here, that's the area of the rectangle. And then we're going to add up all of the areas of those rectangles, and then we're going to take the limit as the widest rectangle shrinks to nothing, the width shrinks to nothing. So if this limit exists, then that is what we call the definite Riemann integral of f from a to b, and we say that f is integrable, and that's it. That's it, Riemann integrable. So hopefully that's a bit of a review. This might be a little more familiar. So it turns out that if f is integrable, meaning it satisfies that previous condition, then what you can do is rather than have all of these non-uniform subintervals, you can choose them to be the same length. So it helps and it's convenient to choose delta x sub I to just be the same length for every subinterval. And then we have an easier formula for delta x. Now we don't need to index it by I because they're all the same. And it's just the length of the interval divided by the number of intervals you want to cut it into. Now you can rewrite the definition like so, and this might look a little more familiar to you, but that's really what it is. Okay, now we can go back to this picture. So how does this machine actually work? Well, it basically makes a whole bunch of approximations of the area under this curve by using rectangles. So each one of these things is the area of this rectangle, and then this would be area of this rectangle, and then the area of this rectangle, and so on and so on. You add them all up, and then what you get is you get an approximation of the area under that curve. Not the exact value, but an approximation. Then what you do is you take the limit as n goes to infinity, and that will give you the exact value as long as that limit exists. And there it is. So that's how the Riemann integral works for for one-dimensional functions or functions of a single variable, right? Now we want to generalize this. So we want to extend this to functions of multiple variables. And what we're going to do is we're going to start with functions of two variables, all right? And the way we're going to do this is we're going to define the volume of a region E in space, which lies underneath a surface defined over some rectangle. So think back to Calc 1. What we did was we found the area of this region under a curve over an interval, right? Now what we're going to do is we're going to find the volume of a region E under a surface on some two-dimensional rectangle. That's what we're going to do now. That's the first step in the generalization. So how do we do this? First, just consider a rectangle in R2. So we'll call it A comma B cross C comma D. This is literally just a rectangle with these as the intervals that make the side. There we go, like that. That's what that is. Here it is written in set builder notation. And now what we're going to do is we're going to suppose that our function is defined on that rectangle. And just for ease, like we did back in Calc 1, we're going to assume that f is non-negative. So f of x comma y is always 0 or positive, just to make things easy. Doesn't have to be, but to make things easy, let's say it is. So what is our goal? We want to find the volume of this region E. What is the region? It's the set of all points in space where z is between 0 and f of x comma y, and the point x comma y is in our rectangle R. That's the goal. So here's a picture of what we're trying to do. Maybe this is a little bit easier. This is actually one of the reasons that I was encouraging you to imagine these three-dimensional objects and just kind of get a feel for what they look like if you were to slice them, because now we're really going to need this three-dimensional comfort, I guess, you could say, intuition for working in 3 dimensions. So here is the rectangle R. This is the surface. And what we want to find is the volume of this region underneath the surface here. That's what we're looking for, okay? That's what we're looking for. So how do we do it? Well, the mechanics of this are very, very similar to what we just saw with functions of a single variable. Put it succinctly, we're going to take our rectangle, we're going to cut it up into a bunch of subrectangles, we're going to pick a sample point in those subrectangles, evaluate the function at that sample point, multiply that by the area of the rectangle, add up all the results, take the limit, and get the exact volume. All right, everybody got that? Okay, here we go. Let's make that a little more precise, a little more rigorous. So first thing we do is divide our rectangle R into a whole bunch of subrectangles. Now we're in 2 dimensions, so we got to subdivide in 2 different ways, right? It's not just an interval, it's an actual rectangle now. Yeah, so how do we do this? We divide this interval a comma b into subintervals x sub I minus 1 comma x sub I with width delta x sub I. And then we're going to divide the interval c comma d into subintervals of width delta y sub j now. We're doing this in generality, so we're not assuming they're uniform just yet. We're going to assume they're uniform in like the next slide. So the point here is the partition does not need to be uniform, but if it turns out your function is integrable, then it can be a non-uniform. I mean, it can be a uniform partition. But this is basically the idea. Now what we're going to do, yeah, there you go. See, in many cases, we can just choose the subintervals to be equal length. And so that way we don't need to index delta x. We can just say that delta x is b minus a over m, and delta y is d minus c over n. So let me zoom into this picture for just a minute here. There we go. That's pretty good. Can't see it so well. Maybe kind of do this. That's a little bit better. Okay. Come here. That's a little bit better. All right. So here is the idea. Here's the interval from A to B. Chop it up into a bunch of subintervals. What are the subintervals? They're this. And because we're going to choose it to be a uniform partition, the length of each one of these subintervals is delta x. Okay. Now do the same thing for this interval from C to D, but you don't need to do, it doesn't need to be the same number of subintervals. That's why you notice here there's an M and there's an N. We don't need it to be the same number of subintervals. We don't need it to be like a square, right? They can be any number. So what we're going to do is we're going to cut this interval up into a bunch of subintervals, and each one of those subintervals has length delta y. And so what you get is corresponding subrectangles. That's what all these are. Subrectangles r sub I comma j. And that's what we get here. So each one of these subrectangles can be double indexed. So r comma I sub j, where I is depending on x and j is depending on y. And this is the how you write it in interval notation, you could say. Now, because we chose the partition to be uniform, the area of each one of these rectangles is delta x times delta y. So quite literally, width times height, or maybe I should say length times width. And then you get the area, and that area we're calling delta A, right? Okay, so let me put the thinker up for just a minute, and I want you to stare at this and kind of ponder what we're doing before we go to the next step where we talk about the sample points. All right, here we go. So next thing we're going to do is we're going to choose a sample point in each one of these subrectangles. That's what all these little dots are that you see. The sample point just needs to be any point in the subrectangle. It doesn't have to be the midpoint, doesn't have to be the upper left corner or the lower right corner, anything like that. It can be any sample point in that subrectangle, r sub ij. And what that's going to allow us to do is it's going to allow us to approximate the part of E that lies above this rectangle and below our surface with a thin rectangular column. So just like we were using rectangles with functions of a single variable, now we are using rectangular columns, like rectangular, I can't make that into a square, rectangular prisms that have a base of our subrectangle, and then the height is the height of f at that sample point. So let me zoom into this a little bit here. There you go. Here's our partitioned rectangle R. Right? I should do 2 sides, sorry. There you go. It's partitioned, it's like a grid. And then for each one of these subrectangles, we're going to pick a point, and we're going to evaluate the function at that point. That's what this height is, right? So the height is literally the value of the function evaluated at the sample point. Then we're going to compute the volume of this column that you see underneath or this column that you see with this piece right here. How do you do it? Well, you just take the height of the column and multiply it by the area of the base. That's how you get volume, right? Base times height, for at least for a rectangular column. So that's what we're going to do. All right, now what is the volume of it? It's exactly what I said. So it's the height of the function times the area of the subrectangle, delta A. Then what we're going to do is we're going to add up all of those columns. So that's what you see happening right here. So for each one of these subrectangles, we get another column. We can compute the volume of that column. Here it is. And then we're going to essentially do a double Riemann sum. This is what's called a double Riemann sum. So we're going to add up these columns and we're going to go from j equals 1 to n. So basically it's like finding this volume right here of this column, this one, this one, this one, this one. And then we're going to do that for each row. Each row you see here. Here, 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 here. That's what this sum is doing. So add up these volumes and then do that all the way down the line. And then when you add all of that up, you get an approximation of the exact volume under this region. There you go. So this is another one where just stare at it. Don't let the notation overwhelm you. I know there's a lot of symbols floating around and there's like asterisks and double indices and double sums. Just take a minute to look at it and let it sit in your brain. In fact, maybe I should even say this. Say it out loud. Like go through this expression and say out loud what every single piece is and say it until it like it clicks in your brain. Okay, now let me kind of say it out loud. Let's see. Well, let me start here. X sub I j star y sub I j star, that's the sample point taken in rectangle R sub I j. What is f of that? F is the height of the rectangle, or the rectangular column, I should say, or just the height of the function, maybe. What's delta A? That's the area of the base. So what is this? That is the volume of the column. Then this says to add up all the volumes in one row, and then this says to do it for each one of those. That's what that formula says, and that will give you an approximation of the volume of the region under that surface. Now, how do we define the exact volume? Well, same way we did in the past. We take the limit as the number of subrectangles goes to infinity, and then if this limit exists, then we can say the exact volume, the exact three-dimensional volume of that region is the limit of these Riemann sums. That's it. Okay, so now hopefully the mechanics here in the construction seem very, very familiar to you and hopefully a little bit more comfortable than maybe they did before, because this is exactly how we define the definite double Riemann integral. But again, we can do this in more generality, so we are going to do it in more generality. So here we go. Let f be a function defined on some rectangle. We're going to let P be a partition of that rectangle R. Here's the partitions in terms of X and in terms of Y. Remember, a partition is just like a set of points. We're going to let delta X sub I be the length of that subinterval. Delta Y sub J is going to be the length of the Y subintervals. We're going to let X sub I star comma Y sub J star. Oops, sorry, that should say it should say ij, little typo right there, be a sample point taken in the subrectangle R sub ij with area delta A sub ij. Remember, it doesn't need to be uniform. Then the definite double Riemann integral of f from A to B, it's a mouthful, is the number given by this symbol. So it's the double integral over R f of x comma y dA. And what is it? Well, it's basically taking the limit as the largest subrectangle goes to 0 in area, all right? Because remember, it doesn't have to be a uniform partition. It's just nice when it is. So provided this limit exists, this is how we define the double Riemann integral over R. And this has to be true for any partition P of R. And if this number is finite, then we say that f is Riemann integrable. All right, so this is the technical definition of the double Riemann integral. Now, again, if f is integrable, then for convenience, you can just choose the delta x sub I and delta y sub j to be uniform so that you get a nice formula for both delta x and delta y, and then a nice formula for delta a sub ij. It's just delta x times delta y. And then we just take the limit as the number of those rectangles goes to infinity. All right, so this definition here and this definition here are equivalent as long as everything is comfortably nice, you could say. As long as your function is integrable, then you can go back and forth willy-nilly. Okay, now here's where things get a little bit more complicated. You'll notice that this Riemann integral is written in terms of a limit. So this double Riemann integral is a limit. And so if you want to be properly rigorous and frankly just mathematically safe, then what you need to do is you need to express this in the formal definition of a limit. And that's what we have right here. So this is the precise definition of a definite double Riemann integral. So we say that a function f of x comma y is Riemann integrable if and only if for all epsilon greater than 0, there's a delta greater than 0 such that this distance is small for all partitions P of our rectangle as long as the maximum of the area of this subrectangle is less than delta, and for all choices of sample points. Whew. Oh my gosh. Okay. All of this is a mouthful, right? So let's make it a little more intuitive because I know there's a lot of symbols flying around here. Intuitively, this is what it's saying. It's saying that the integral can be approximated to any degree of accuracy by a double Riemann sum as long as the number of rectangles m times n is chosen to be sufficiently large, or in other words, that the largest area is less than delta. So when you see an inequality like this, just think of it in terms of approximations versus exact values and associated errors. This is the exact value. This is an approximation. Notice there's no limit here because this is the formal definition of a limit. This is an approximation. So pictorially, this thing is representing this. All right, that's what that's representing. Let me go back to it. That's this piece right here. And what we're saying is that this is the exact value. This is the exact volume of that region, right? And here we're saying that the difference between the exact volume and the approximation is small. Small. This is the error associated. This is literally the difference between the approximation and the exact value. And we say a function is Riemann integrable if it doesn't matter how big the tolerance is, or really how small the tolerance is, we can always find an approximation that is within that tolerance. And if you can always do that, then your function is integrable. Whew. Okay. If you have questions, we can talk more about it in class, but let's get to some examples. So let's do this. Let's estimate the volume under the curve given by this equation on the square 0, 2 cross 0, 2. We're going to use 4 subsquares, and we're going to pick the upper right corner of each square for our sample point, okay? So this one I do want you to try on your own, so think about it for a minute. And then, as usual, say something out loud, either to yourself, to your dog, to your sister, your brother, your friend, your group mates, somebody, just to kind of give yourself that oral feedback, that audio feedback. Okay, and now you try it on your own. And what I want to be clear about is you're just doing an estimate. You're not computing the exact value of the volume. You're just doing it, you're doing an estimate. Okay, now let's do it together. All right, so here is our rectangle. We're going to cut it up into 4 subsquares, and then we're going to pick the upper right corner of each square. So pictorially, this is what it looks like. Here is 0, 2 cross 0, 2. We are going to cut it up into 4 equal-sized subsquares. This is the here, I'll do this. This is the subsquare R11, R12, R21, R22. So we can find the area of each one of these. It's going to be the same area. And then what we're going to do is we're going to basically pick these sample points in our subsquares, and that's where we're going to evaluate the function, this function f of x, y equals z. So we're going to take this point and plug it in, this point and plug it in, this point and plug it in, this point and plug it in. There we go. And this is what it looks like three-dimensionally. So this is kind of a nice picture because you can see the actual surface here, and then you can see our approximation. So our approximation is these columns that you see right down here, and here are the sample points. There you go. So in this case, we're going to get an underestimate. Just happens to be because of the shape of the function and because of the sample points we chose. All right, so that's not too bad. We know our formula. We're going to add up four different values. So we're going to evaluate the function at 1, 1, multiply it by delta A, evaluate the function at 1, 2, multiply it by delta A, 2, 1, 2, 2, add it all up, and we're going to get an estimate of 34 units squared. The area of each one of these subsquares is 1. This is delta A in each case. And you can also see that in the picture here. This is a 1 by 1 square. It's a unit square, so its area is 1. All right, so 34 is an estimate of the volume. It's not the exact volume, but it's an estimate, and it's a pretty rough estimate, right? Let's look at some comparisons. Now, we were getting 34 for this, but it turns out that if you add, well, we did 4 subsquares, right? Well, here's what it would look like if you did 16 subsquares. So in this case, you're cutting up that single square into 16 smaller squares and then picking what did we pick? The upper right corner? Yeah, that's right. There we go. So this is what it looks like if you pick 16 subsquares. This is what it looks like if you use 64, and this is what it looks like if you use 256. And what I want you to notice is, notice how the approximations become more exact as the number of subrectangles or the columns, right, is increased. So I like to think of it as a pixelation, and maybe we'll talk about that in class as well. But this is like a really, really pixelated version of the region. This one's a little bit less pixelated. We made the pixels smaller in size. So we're getting something that doesn't look as jagged, doesn't look as polygonal. Here we shrunk the pixels down even more. And the process of approximating an integral means you keep doing this ad infinitum. And if your function is integrable, it will eventually give you the exact value. It'll give you the exact value. All right. So moving along here, as you can tell, we have our choice of sample point, but it is common to pick the midpoint just for ease, once again, just to pick the midpoint. So this is just the formula restated, except in this case, we're using the midpoint rule, which means we pick the midpoint of those subrectangles. So x sub I bar is the midpoint of x sub I minus 1 comma x sub I. And y sub j bar is the midpoint of the subintervals in terms of y. So no problem picking the midpoint. All right. Okay, so now the real question is, we would like to be able to evaluate these integrals, right? And so this is where we need to start talking about iterated integrals. We're going to arrive shortly at one of the most useful theorems in multivariable calculus. It's called Fubini's theorem. But let's get there, okay? Let's get there through a process. So we saw previously that computing integrals using the limits of Riemann sums is tedious and difficult. So I'm assuming your Calc 1 professor did this at some point where it was like, oh, find the Riemann sum and then take the limit as the upper index goes to infinity, right? And this can be really, really tedious and really difficult. You might have had to use the formula for the sum of the first positive integers, the first n positive integers, or the formula for the sum of the first n squares of the positive integers. And you just have all these limits, and it's really, really difficult and tedious. So this was the beauty of FTC2. This is why everybody loves Fundamental Theorem of Calculus Part 2, because it basically lets you evaluate an integral without having to do this. So this is why everybody was so excited when FTC2 was discovered, because it basically said if you have an antiderivative of your function, you can just evaluate it at the endpoints of the interval, take the difference, and then that'll give you the exact value. Saves you all of this pain, right? Here's the catch. FTC2 only applies to single variable functions. So if you recall FTC2 from Calc 1 and Calc 2, those are functions of a single variable, and you would evaluate like, f of b minus f of a, capital F of b minus capital F of a, right? How do we do that with double variable functions, functions of two variables, right? So we're going to address this through what is called iterated integration. when it is possible to do so. So we need a couple of definitions here. The first one is what's called partial integration. So let me read this one out loud. Suppose you've got a function of two variables, and it's integrable on the rectangle a comma b cross c comma d. Then we're going to write this symbol to indicate that x is held fixed, and we integrate with respect to y. All right, so the differential is important, and I'm hoping that your previous calc instructors, harped on you about including the differential. The differentiable is not negotiable here. You have to include it so we know what you're talking about. So this is saying integrate the function f with respect to y, and just hold x as a constant. Kind of the same thing we did for partial differentiation, right? It was like, oh, just pretend x is a constant and then differentiate with respect to y. Now we're doing the same thing, but with integration. Just pretend x is a constant and integrate with respect to y. And this process is called partial integration with respect to y. All right? So just one more time, I want you to kind of stare at this symbol and notice that y is the only variable here. Y is the only variable. X is being held fixed. Okay, all right. Now let's talk about iterated integration. So what is iterated integration? So this thing here, this integral we just saw a moment ago, that's just a number, but it's a number that depends on the choice of x. So we fixed x and then integrated with respect to y. So that defines a function of x. So we can actually write this as a function of x and call it, a of x, for example. And we're going to say a of x is this integral. All right. Now what we do is we're then going to integrate the function a of x with respect to x, like that, like that. And that gives us what's called an iterated integral. So if we integrate this a of x function, well, a of x is literally just equal to this integral. And then now we can drop the parentheses and just write it like so. And this is a double integral over a rectangle, but more importantly, it is an iterated integral. It is saying how to integrate with respect to y and then integrate with respect to x. All right? So that's how we're going to do these double integrals. We're going to do it in an iterated way. So let's try an example. Here we go. This one I want you to try on your own before we go through it. So evaluate this double integral, the integral as y goes from 1 to 2 and x goes from 0 to 3. Of x squared y. Okay, so look at this for a moment and think about how you would start. All right, now say something out loud about how you're going to start. What are you going to try first? All right, and now try to work it out on your own, and we will do it together in just a moment. All right, here we go. All right, so first thing is notice that this inner integral is with respect to y, right? You see that? So the differential here is critical. It's telling us what we're going to integrate with respect to, right? So we're going to integrate this function with respect to y, holding x squared as just a fixed value. And then once we have that result, we can apply FTC2 to that result. And then we will get another function that only depends on x at that point. Then we're going to integrate that resulting function with respect to x and use FTC2 to evaluate it at these endpoints, the antiderivative. So here's what it looks like. And I'm gonna walk through it carefully, but this is the process we're gonna see a lot throughout the rest of the chapter and throughout the rest of the course. So you do wanna get comfortable with this. Looking at the integral, I'm sorry, the inner integral first, just pretend this is an integral with respect to y. Antiderivative of y is y squared over 2. And now we're going to evaluate this function at 1 and 2 and take the difference. This is the application of FTC2. Right? When you do that, you end up with this right here. So this inner integral is actually equal to this function. Now we're going to integrate this function with respect to x. So here we go. This thing now becomes this iterated integral, which we just found. And now we're going to do this integral with respect to x, apply FTC2, and boom, there it is, 27 over 2. That's it. So you could think of it like this. The volume of the region underneath this surface on this rectangle is equal to 27 over 2. All right, now we're going to change things up a tiny bit. I want you to try to do this one on your own too. And all I'm going to point out is notice that what we did was we changed the iteration of the integrals. So notice the order here is different. I'm going to flash back and forth a couple times. All right. And I want you to try to do this one on your own too. I'll just jump straight to the writer here. Try to work it out on your own, and then we'll do it together in a moment. All right, here we go. So process is the same, except now our inner integral is going to be integrated with respect to x. So here's what we get. Evaluate this with respect to x. We get this, just a simple power rule for antiderivatives. Apply FTC2, and now what we're left with is a function of y only. And then now we can integrate this with respect to y, use FTC2 again, should say, well, 9 times that, clean that up a little bit, and we get 27 over 2. So that's kind of cool. We actually got the same result. Why? That's the question. Why? And who says? Do we always get the same result? Does it not matter what order we integrate? What is going on? Because that would be nice to know, right? If we knew that it wouldn't matter, that would be great to know. Well, this is where we're going to get our important theorem, Fubini's theorem. So this just kind of reiterates, you could say, what I just said. We got the same value in both cases, despite integrating in a different order. So this behavior is kind of like Clairaut's theorem, if you remember the one about the mixed second partial derivatives and how if they were continuous, then they had to be equal, right? Um, this is basically it. So just like with Clairaut's theorem, if there was a condition met, then we would get equality. So here, if there's a condition met on those functions, then we can integrate in either order. And this is what's called Fubini's theorem. One thing I will say is this is a version of the theorem that is specifically tailored for this multivariable calculus. Fubini's theorem is actually a more general theorem about, frankly, just Lebesgue integration. So some of you will learn about this when you take a course in real analysis, and you learn about measure theory, and you learn about the Lebesgue measure, and then you learn about the Lebesgue integral. But for our purposes, this is Fubini's theorem for this class and everything that we're going to talk about related to multivariable functions and multivariable integration. So here is the condition. If f is continuous on a rectangle, then you can iteratively integrate the integral, or iteratively integrate the function, and it doesn't matter which order you do it in. All right? That's Fubini's theorem. So Fubini's theorem says a couple of things. For one, it says you are allowed to integrate iteratively. And the second thing it says is you are allowed to change the order of integration. However, there are two very important conditions here. The first condition is the region of integration has to be a rectangle. Okay, so this is a big one. So do not forget this, because it's very easy to forget. You can't just switch the order willy-nilly unless the region is a rectangle. All right, keep that in mind when we get to the next section. The other thing is that our function needs to be continuous. So we need a continuous function defined on a rectangle. Then we can iteratively integrate, and it doesn't matter which order we do it in. We'll get the same result. Okay. A little bit more generally, this theorem actually holds if we only assume that f is bounded on the rectangle and discontinuous only on a finite number of smooth curves, and that the iterated integrals exist. But for our purposes, we'll just say f is continuous to save us some work. All right. Okay. Here's a picture of what it looks like. So yeah, Fubini's theorem visualized. What Fubini's theorem is really saying is that as long as your function is continuous and you're integrating over a rectangle, then it doesn't matter how you scan the region. I'm going to say this a lot from now on, but the integral is like a scanning machine, and we have to tell it how to scan. I'll say this a lot in the next section, actually. But Fubini's theorem is saying, hey, if you're integrating over a rectangle, you can scan in either direction first and then scan in the other direction second, and you'll get the same result. So here's that a of x function. So here we integrated with respect to y first, and then for each one of these, we get a slice. and that slice has a certain area. Now what we're going to do is we're going to add up all the slices as x goes from A to B. Fubini's theorem says you could slice it this way first and then add up the slices, or you could slice it this way first and then add up the slices. Either way, you will get the same result. Pretty cool, huh? And I think this makes sense, right? It's nice and intuitive there. Oh, it doesn't really matter if I slice it this way and then add up, or slice it this way and add up, I get the same. As long as it's a rectangle, and as long as my function isn't behaving weirdly, then everything's good. Okay, all right, so here's another one I want you to try on your own, and then we will do it together. I want you to evaluate this double integral over the rectangle R, and in this case, this is the rectangle R, all right? So think about how you would try this one. Notice this is dA, right? Okay, now say something out loud. What do you think you would do first? What do you have to figure out first? Okay, and once you've figured that out, write it down, try to work it out, and we will do it together in a moment. Okay, so the first thing you should be kind of scratching your head over is what do I integrate with respect to first? I mean, this is just dA, change in the area, right? Do I integrate with respect to x? Do I integrate with respect to y? Well, this function's continuous, and this is a rectangle, so Fubini's theorem basically says it doesn't matter which order you integrate with respect to first. You get to choose. So here I chose to integrate with respect to y first. There we go. So I'll do this integral with respect to y. Here we go, FTC2. Then I will do the resulting integral with respect to x. Here we go, FTC2. And voila, at the end, that is what the double integral gives, -12. Pretty cool stuff, huh? It's not too bad. It's not too bad. One note I'll say, I guess I don't have it written on here. Hold on a sec. Let me check something. Yeah, one note I will say, and this is a good thing to keep in mind, as you go through this iterated integration process, the functions that result should only depend on the variables that remain. Okay, so I want that to be clear. Like you shouldn't go through this process and still have y's. So if you go through this first integration process and your result has a y in it, you did something wrong, guaranteed. Because each one of these steps is an iterated integration. So you should be essentially eliminating a variable through this process at every step. That's why here we only have x's involved. Okay. All right, here is another one. Okay, try this one on your own, and then we will talk about it together in just a moment. Yeah, here, I'll throw up the writer. There you go. Try it on your own, and then we'll do it together. Okay, what do we got to do first? We got to unpack what this says, right? So here we're going to find the volume of the solid that's bounded by this elliptic paraboloid, the planes x equals 2, y equals 2, and the 3 coordinate planes. Okay, so, well, we can write this as a function of x and y, and that'll be like our surface, right? These are going to give us some bounds, and then the coordinate planes are going to give us some bounds, and we're definitely integrating, excuse me, over a rectangle. So let's see what we get. All right, so this one, yeah, the 3 coordinate planes. So the rectangle that we're integrating over is 0, 2 cross 0, 2, and this is the surface. So I basically just solved this equation for z, and this is the surface, which we can write as a function of x and y. This function is continuous on that rectangle. Why is that? Why is this function continuous? I'll leave that for you to answer. So because it's continuous and we're on a rectangle, that means we can use Fubini's theorem and we can integrate iteratively. So here we go. The volume of this region is the double integral over that rectangle R. We can choose the order of integration. In this case, it doesn't really matter which order. It's going to be, there's no easy thing, or it doesn't make it harder or easier no matter whichever way you do it. Oh my gosh, I just stumbled over that badly. It doesn't matter if you choose x first or y first. The result will be just as easy to calculate. There we go. So Looks like I did x first this time. So I'm integrating this with respect to x. Here we go. Apply FTC2. Now I've got a function of y only, and I'm going to integrate with respect to y. Apply FTC2, and then the result is 48. So the volume of this region is 48. Pretty cool stuff, huh? It's kind of fun once you get the hang of it. Now I'm excited to share this with you. So this is like, man, every Calc 1, Calc 2 student's dream that you could never really fulfill. And now there's a version of it that we can fulfill. So it turns out there's a very, very satisfying corollary to Fubini's theorem. And it's this. So in the very special case, this only works for these very special cases. So you can't get too excited. But in the very special case where our function f can be factored as a product of a function of x only and a function of y only, we get the following very satisfying result. Here we go. If we can factor f of x as a function of g that is, sorry, as a function g that is strictly with respect to x, and a function h that is strictly with respect to y, well, then Fubini's theorem says that we can basically integrate iteratively, right? But that means that to this integral, h of y is considered a constant. And we have linearity of the integral, which means we can pull this entire function out, like so. And then what we get is this. We get a product of integrals, one with respect to x, one with respect to y. So what is the satisfying corollary? It says this. If your function f can be factored into the product of functions g of x times h of y, and g only depends on x, and h only depends on y, only being the key word here, then the double integral can be broken into a product of integrals. So this is like I said, this is like the dream that everyone has in Calc 1. Can I just take this integral and write it as integral of a product is the product of the integrals? In Calc 1, the answer is no. And in Calc 2, the answer is no. But in Calc 3, the answer is yes, if these functions are basically totally disjoint in terms of their input variables. So if this is strictly a function of x, and this is strictly a function of y, then we can split this double integral into the product of two separate integrals. Wah! Pretty cool. But beware, it only works in these cases. So it doesn't mean you can just start pulling integrals apart over products. You can't do that. That's not allowed. Only in these very, very specific cases. So that might feel like a bit of a cop-out, but these types of cases come up a lot. So here's one that I want you to try on your own at home using this very, very satisfying corollary, and you'll see what I mean. So look at it for a minute. And I would say something out loud, but I'm pretty sure you already know what you would say. So jump right into it and see if you can calculate it on your own. All right, now let's do it. So first thing is we're integrating over a rectangle. And this function here is definitely a continuous function because it's a product of continuous functions. So it's continuous. So Fubini's theorem says we can integrate it iteratively. But the best part is that this here is only a function of x. And this here is only a function of y. So we're going to be able to take this double integral and split it into a product of two single integrals. Here we go. This is what it looks like iteratively. Because this only depends on x and this only depends on y, we can split it up directly into a product of two integrals, one with respect to x, one with respect to y, and then treat them as single integrals. Boom. FTC2 on this, FTC2 on this. We get 1 in both cases. 1 times 1 is 1. Hooray! Love it. Okay. All right, so we're nearing the end here. Last thing we got to talk about is average value of a function. So this is something that's, again, it's like a generalization of something that you saw back in Calc 1, right at the end, or maybe near the beginning of Calc 2, in sections 5.5 for this book. So we found the average value of a function of a single variable over an interval a comma b, and this is how it's defined. So if you want the average value of a function, this is the formula that you used. But this formula makes a lot of sense if you think about it in the context of averages, right? So what we're doing is we are adding up all of the values of f of x, and then we're dividing by the number of values, or in other words, the length of the interval. So this is kind of like finding a continuous average. You remember like averages when it was discrete was like add up all of the numbers and then divide by how many of those numbers you had? This is the same idea, except now we are continuously adding up these values and dividing by this length, which is kind of like a continuous number. Very, very hand wavy. That is not mathematically precise, but this is what's happening here. If you want the more precise derivation of this formula, or the derivation of this this formula, it's pretty nice. It's in section 5.5. Okay, so now how do we generalize this to functions of two variables and then later on functions of 3, 4, 5, and many variables? Here's how. So let f be a function of two variables defined on a rectangle R. We're going to let a of r be the area of that rectangle. Then the average value of f on that rectangle is just the integral of f on that rectangle divided by the area of the rectangle. So this makes sense, right? It's very, very similar. It's just adding up those values and dividing by the area. For single variable, it was adding up these values and dividing by the length. And that's how we got the average value. So this is the average value of a function of two variables. Put another way, you can say that the integral itself is equal to this product. This is actually just a regular multiplication. In fact, maybe I should, sorry. Pretend that's just scalar multiplication. So if you take the area of the rectangular base and multiply it by the average value of f, you get the integral back. That's what it's saying. Let's get a little more intuition. So geometrically, what this is saying is that the box with a base of r and a height of f average has the same volume as the region that lies under the graph of f. So the graph of f in this case would be like this mountain range that you see here. And this box that you see has the same volume as that mountain range underneath the area, the region underneath that mountain range. That's what I'll say. And yeah, in this picture, the water line is basically at f average. There you go. That's that height. Cool stuff. What I usually say in Calc 1 is if you pretend you're like a higher dimensional being that can control gravity, like in Interstellar, right? Pretend you could take this and you could like hold it up, and I could pull some of the function up and I could push some of the function down. I have full control over this, right? Well, if I were to suddenly release control, the region would kind of and settle and it would flatten out, right? That's what this is. That's what that is. Okay. All right, so find the average value of this function, x squared y, over the rectangle with these vertices. And this is one that I want you to try to do on your own first, and then we'll do it together. Shouldn't be too bad, right? Maybe say something out loud about what you might try to do first if you need to find the average value. What's something you need to know to find the average value? All right, now go ahead and calculate it, and we'll do it together in a moment. Nice. Okay, here we go. So if we want to find the average value of a function over some rectangle, we need the area of the rectangle first and foremost. So we need to find the area of this. In this case, it can help to draw a quick sketch of it. I don't have one on my slides, but it's not too hard to sketch. I'll just do a very rough sketch. Okay, -1, 0, so there's one. -1, 5, 1, 5, and then 1, 0. So here is the rectangle that we're integrating over. And what is its area? Well, this is length 2, and this is length 5. So the area of our rectangle is 10. Right? Is that right? Let me see. 1 to 5. Yes. Okay. There we go. All right. So now that we know the area of the rectangle, we can do our double integral. And it's a rectangle. Our function is continuous, so it doesn't matter the order we integrate. We can do this iteratively. And then voila, you just go through it. 1 over 10. Here we go. Apply FTC2 with respect to y. Get a function of x only. Apply FTC2 again, and you get 5/6. There it is. So average value isn't too bad. It's pretty much just finding the area and then dividing by the area. That's it. That's really it. And on that note, let's play. So I'm excited to do this in the activity with you all. I think that's about it. Don't want to ramble on too long. In the next couple sections, what we're going to do is we're going to generalize this integration process to regions that aren't just rectangles. 15.2 will be general regions, and 15.3 will be polar regions. So that's kind of cool. All right, until next time, have a good one, and thank you for listening.